Dear students, today we are going to derive an expression for the refractive index of a liquid. Say, for example, we have taken water with respect to air, and this expression we will derive by using a convex lens and a plane mirror. How we are going to set up the experimental arrangement is shown in the figure. We place a convex lens made of glass material, place it over a mirror, and then we fix a object pin on the top of this lens and adjust it such that the image of the pin is formed at the same place where the pin is placed. This will be obtained by removing the parallax. The image and object starts moving all together. That's it. That height we will measure, and that will give us the focal length of the plane mirror. Focal length of the convex lens. How we can say like this? Here you see there is a basic concept that light retraces its path. Now a ray coming from focus will become parallel after refraction. Say we have a convex lens and ray is coming from focus. After refraction it will become parallel to the principal axis. And if we place a mirror over here, what will happen? The ray will be incident normally on the plane of the mirror, and if a ray is incident normally, it will retrace its path, it will return on the same path. And so, according to the principle of reversibility of light, these light ray will again meet at the same point from which it originated, and therefore we find the focal length of the convex lens. Now in the second experiment, what we do is we place some water on the surface of mirror so that the gap between the lens and the mirror is filled with water, and once it is done, a plano-concave lens of water is formed. This plano-concave lens formed by water will also act like a lens, and the combined focal length of the convex lens and the water lens could be found in the same fashion as we have found the focal length of the convex lens. Again we shift the pin to some different height and shift it such that the image of the pin is formed at the same place where the pin is placed, and this is ascertained by removing the parallax. And so that position of the pin where parallax is removed, the height of that pin from this mirror surface will be equal to the equivalent focal length of the combination of water lens and the glass convex lens. So bearing all these things in our mind, we will proceed how to do the calculation and do the mathematical work to find the expression for refractive index of water. Here we used water, and the refractive index of water will be found. Instead of water we can have any another liquid, so that we can find the refractive index of any another liquid as well. Here we have a combination of two lenses, so the combined focal length, this is distance of f2m, length of f2m, focal length of the combination of two lenses 1 by f will be equal to 1 by fg plus 1 by fl, where fg is the focal length of the glass lens, convex lens, and fl is the focal length of water lens. L refers to liquid and G refers to glass, and therefore we can write 1 by FL equal to 1 by F minus 1 by Fg. We call it equation number 1. Now using the lens maker formula, we have focal length of water lens given by refractive index of water with respect to air minus 1 and bracket close and another bracket start 1 by R1 minus 1 by R2, where 1 by R1 is the radius of curvature of the first surface of the plano-convex lens. This is the first surface, and another surface, plane surface, is second surface. Now for the second surface, radius of, since it is a flat surface, second surface of water lens, therefore R2, that is the radius of curvature of second surface, will be infinity, and therefore we place over here infinity, and therefore 1 by FL becomes equal to mu L A minus 1 in within bracket into 1 by R1. So this is we call it equation number 2, where R1 is the radius of curvature of the first surface of plano-concave lens, water lens. Now again, using the same lens maker formula, for the glass lens, we have 1 by Fg equal to refractive index of glass with respect to air minus 1 within bracket, another bracket start 1 by R1 minus 1 by R2. Well, R1 is the refractive index of radius of curvature of the first surface of the glass convex lens, and R2 is the radius of curvature of the second surface of the glass lens. But here in this case, radius of curvature of the first and second surface of the glass lens are taken to be same, that is equal, and say it is R1. Therefore we can write equal to refractive index of glass with respect to air minus 1 within bracket, and 1 by R1 minus 1 by R2. Here you see one radius of curvature will be minus, so minus of minus becomes plus. You can see it separately. Well, if you take one radius of curvature as positive, because for that you need to measure in this particular direction, then radius of curvature of the other surface must be negative, because you are measuring it while moving against the previous direction of movement. And so if we take R1 as positive, then R2 will be negative, and so we have, and since the magnitude of radius of curvature are same, therefore we have 1 by R1 minus 1 by R1, that becomes 2 by R1. And so we have, and also we take refractive index of glass equal to 1 minus 1.5 minus 1, that becomes 0.5, and so it becomes 0.5 into 2, that is 1 by R1, and therefore we can write 1 by Fg is equal to 1 by R1, 1 by Fg is equal to 1 by R1, and therefore we can write Fg is equal to R1. We call it equation number 3. And from equation 2 and 3. Here you see this is equation number 2. We have got the expression for 1 by FL, and here is the equation number 3. We got the value of R1 in terms of Fg. So we write 1 by F. You see in this expression for R1 we can write Fg. So for R1 we can write Fg in this expression, and since for the plano-concave lens, this upper surface, first surface of the lens, plano-concave lens, will be negative, because you are making measurements, you have the concave surface, so you are making it and getting minus sign using the sign convention. So we write 1 by FL equal to mu L A minus 1 by R1, but for R1 we write, we have taken minus sign according to sign convention, so we write mu L A minus 1 divided by minus Fg, and so minus sign is carried on to the numerator. So what we get is, mu L minus 1 upon Fg equal to 1 by, here you are using this relation 1 by FL. 1 by FL is equal to 1 by F minus 1 by Fg, and so we get, on solving this, we get refractive index of liquid with respect to air is equal to 2 minus Fg upon F. Here you see that the expression is in terms of, here you see that the refractive index, we have missed this sign over here, the refractive index of liquid with respect to air, on solving this expression, gives us equal to 2 minus Fg upon F, where Fg is the focal length of the glass lens, and F, capital F, is the focal length, the length of the combination of glass lens and water lens. So this expression is quite helpful in doing numericals at times, and also remember that these theoretical exercises are very helpful and gives us the skill to solve numerical problems as and when it comes. That's all for today. Thank you and have a nice day.